In this video, we will introduce you to our new reference design, the high-performance e-scooter brushless DC motor driver. Motor drivers for modern low-power e-mobility applications like the e-scooters and small e-bikes pose new challenges for developers. The battery size of these applications is limited, and the motor driver must provide high efficiency to maximize the battery life. A low form factor for the motor driver is mandatory as space is at a premium. Low operating acoustic noise and regenerative braking capability are two common requests, especially in the crowded urban environments. These are, in general, cost-sensitive solutions. The high-performance e-scooter BLDC motor driver solves these challenges and is ideally suited for low-power e-scooters and e-bikes. At only 60 mm in length and 50 mm in width, this is a low form factor design. The board is equipped with a powerful digital signal controller and can run the most demanding motor control algorithms like field-oriented control or FOC. The driver supports sensored or sensorless motor control applications and delivers sinusoidal phase currents, resulting in a very low operating acoustic noise. The motor phase currents are measured using 3 low-side shunt resistors. Regenerative braking is also supported, and the bill of materials is optimized for space and cost. This is the block diagram of the motor driver. In the top left corner is the buck regulator based on the MCP 16331 switcher. This regulator provides the 12-volt bias voltage for MOSFET drivers. 2 low dropout regulators provide the 3.3 volts for the DSC and 5 volts for the Hall sensors of the motor. The MOSFETs of the power inverter are driven by 3 MIC 4104 MOSFET drivers. The application is controlled by the DS PIC33 CK64 MP105, a powerful DSC that also includes advanced analog peripherals like the high-speed operational amplifiers and comparators. Motor phase currents are sensed using 3 low-side shunt resistors. The current sense amplifiers are implemented using the DS PIC33 CK internal operational amplifiers for space and cost saving. This is the top of the board with the input connector located on the upper side. Here is the 12-volt bias generator implemented using the MCP 16331 buck regulator. The MOSFET drivers are located in the center of the board. There are also high-side power MOSFETs, tab output connectors, and I/O connectors located to the left side of the board. On the bottom of the board, the low-side power MOSFETs and the current sense shunt resistors are located to the left. The 5-volt and 3.3-volt bias voltage generators are located to the upper right. And here is the DSC and the additional circuitry for current sense amplifiers. The input voltage range is between 18 to 42 volts, covering applications powered from lithium-ion battery strings up to 10S. The board is capable of delivering up to 15 amps RMS current for long-term and up to 27 amps RMS current for short-term. The driver delivers up to 250 watts of continuous power and up to 800 watts of peak power. The PWM frequency range is from 8 kHz for large inductance motors to 50 kHz for low inductance motors, and the maximum duty cycle can reach up to 99%. The driver also offers protection for motor phase overcurrent, input under and over voltage, and over temperature of the power inverter. Let us see some waveforms taken during our testing of the board. This is the phase current. A 250-watt e-scooter hub motor was used during this test. The driver produces high-quality waveforms resulting in a very low acoustic noise and excellent power factor for the motor. Here is the input current. A low input current ripple offers multiple advantages. It improves the life of the bulk electrolytic capacitor, which is a critical component for a motor driver, and greatly reduces the EMI. The regenerative braking improves the battery life and may greatly reduce the wearing of the mechanical brake system. This is the battery current during acceleration, constant speed running, and regenerative braking phases. The energy is stored in the so-called flywheel effect during the acceleration and constant running phases, and is delivered back to the battery during the regenerative braking phase. The area under curve is a measure of the stored energy and must be similar for the acceleration and regenerative brake phases. This is the phase current during startup in censored mode. At very low speeds, the rotor position is provided by the Hall sensors, and the driver applies the 6-step commutation strategy. After several transitions of the Hall sensors, the driver is able to interpolate the rotor position using linear interpolation. The phase current becomes sinusoidal, and the motor accelerates. At higher speeds, an angle observer provides the rotor position with high resolution and accuracy for best efficiency and low operating acoustic noise. Let us now see the driver in action. This is the setup used during our short demo. The original motor driver of a commercial e-scooter was replaced by the high-performance e-scooter BLDC motor driver reference design. The motor has 250 watts, and the battery provides 36 volts nominal voltage. This reference design offers high efficiency, low form factor, regenerative braking capability, and is a cost-effective high-performance solution for modern low-power e-mobility applications. We hope you have enjoyed this demonstration. Thanks for watching.